Hi everyone, I'm Shihui, a PhD student at the University of Iowa. Today I'm going to introduce our work, Rethinking Graph Data Placement for Graph Neural Network Training on Multiple GPUs. Graph Neural Network, also known as GNN, now is the state-of-the-art model for machine learning tasks on graphs. GNN plays an important role in many application domains, such as content recommendation, traffic prediction, and so on. Different from the traditional graph processing algorithms, GNN makes predictions on graphs with no features. For example, if we have a social media network with 6 users, the network can be regarded as a graph, and each user is a node on the graph. Because users have many features, for each node, we use a vector to represent the feature of it. The basic operation in a graph neural network is feature aggregation. For one node, aggregation means updating the representation of this node using a function to combine the features of its neighbors and also itself. The basic idea of graph neural network is to learn a vector representation of each node by recursively aggregating the features of neighbors. In each hidden layer, we do the feature aggregation for each node. After all layers updating, we can obtain the final representation, or we can see the embeddings of each node. And these embeddings can be used in downstream works. However, in every layer, if we aggregate all the neighbors' information for each node, the computation overhead will be large. For example, in this graph, if we want to obtain the representation of node 2, we need to aggregate the information of all its neighbors from node 1 to node 5 in the previous layer. And however, the representations of these nodes relies on the nodes in the input layer, so that the number of nodes involved in the computation is exponential, and the computation overhead will be large as the layers increase. Therefore, we need to reduce the computation by using sampling-based GNN training. The idea is to sample a subset of neighbors and estimate the aggregation results based on the sampled nodes. Currently, graphs become larger and the features of each node may contain hundreds or thousands of attributes, so that a graph cannot be stored on one single GPU. To support large graphs, a straightforward approach is multi-GPU training. It means that we partition the graph and distribute the node features onto multiple GPUs. Here are two current GNN systems that support multi-GPU training. The first one is TGL. It assumes that a graph can be entirely stored on multiple GPUs, so that the features will not be stored on CPU. And it adopts matrix partitioning, and so that for each GPU, it will save the partitioning method from matrix. And during training for each GPU, it can load features from its local memory and the other GPUs. PyGraph use a heuristic partitioning method based on training nodes. For large graphs that exceed the memory capacity of GPUs, it stores the graph on CPU and buffers the most frequently accessed nodes of each partition on GPUs. And because the nodes on each GPU are the same, so during training, PyGraph will load data from its local memory and CPU instead of loading data from the other GPUs. And to evaluate the performance of these two methods, we did an experiment on them. We assume that the GPU memory is small and we can only store 20% of nodes on each GPU, so that the rest of the nodes will be saved on CPU. And we use 2 and 4 GPUs for testing on Reddit and Yelp graph. We can see that on Yelp, with 2 GPUs, The data loading time of both paragraph and DGL takes more than 40% of the total execution time, and DGL is slightly better than paragraph. When using 4 GPUs, DGL will save 80% of the nodes on GPUs. And because paragraph save the same set of nodes on each GPU, so even using 4 GPUs, paragraph can only save 20% of the nodes on GPUs. And we can see the execution time and the total time decrease using 4 GPUs. However, the data loading time still takes about half of the total execution time. And the results are similar on Yelp. So we can find that loading feature is a bottleneck of training. Based on the observation, we propose a performance model. We store the graph on CPU and maintain a buffer on each GPU. The nodes on each GPU are not all the same, so they can load for one GPU. It can load feature from local memory, CPU, and also the other GPUs. For each GPU, the cost for function can be written as this formula. In this formula, the Ri represents the nodes that GPU I needs to read from CPU and the other GPUs. And BGPU means the nodes saved on all GPUs. The CCPU means the cost of reading a node from CPU, and CGPU means the cost of reading a node from another GPU. And because of the hardware setting, we may have different CCPU and CGPU. So we need to think about two situations. When CPU is larger, we need to store nodes on GPUs to decrease the cost. So the cost function should be the cost of reading nodes from CPU and also the cost of reading data from GPUs. But when CGPU is larger, we need to read all nodes from CPU. So the cost function is only the cost of reading data from CPU. And for all GPUs, the optimization problem can be written as this formula. Given a buffer with a fixed size, because we train GNN in parallel, so what we want to do is to minimize the maximum cost among all GPUs. So our goal is to find an optimal configuration of BI, which is the nodes that should be saved on each GPU. When CGPU is larger, the optimization problem can be written as this formula. And I said here is all the nodes GPUI need to read, and BI is the nodes that saved on GPUI. And so Ri can be represented by this, and we can further write this formula into two parts. Because the first term is fixed, so when this expectation is maximized for every GPU, this formula can achieve the minimum value. And this means the nodes a GPU need to read from local memory. So intuitively, if we want to achieve the maximum value, we need to store nodes with the highest sampling probability on it. So here comes to our rule 1. And when CPU is larger, the optimization problem can be written as this formula. And similar to case 1, we can write the formula and get 3 terms. The first term is also fixed. So what we need to do is to minimize the last 2 terms, which means maximize the 2 expectations. CCPU here and CGPU is constants, we know that. And the expectations of the second term indicates the number of nodes on all GPUs. So we should which means that we should store as many nodes as possible on all GPUs. And the last expectation is the same as case 1. So each GPU should store the same set of nodes with the highest sampling probability. So here is a trade-off between the we then design an algorithm to explore this trade-off. Our algorithm has mainly two parts: initialization and replacement. We will first initialize the nodes on each GPU follows the last term of this formula, which is to store the same set of nodes with the highest sampling probability on each GPU. And the rest of the nodes will be saved on CPU. Then we use the rest of the nodes on CPU to replace the current nodes on GPUs. We also sort them according to the sampling probabilities. And for each replacement, we need to know whether it is beneficial. So let's see how the cost changes if we replace one node on GPU I with a node on CPU. For GPU I, the last two terms are both changed, because if we replace one node on GPU, replace one node on GPU I with a node on CPU, this term, because the GPU I will read the old node from other GPUs instead of from its local memory. So this term will increase. And for the last term, because the old node in BI is replaced by a new node, so this term will be changed also. And we can describe the changes of the last two terms here. So now P is the sampling probability of one node. And so the increase of the second term can be written as this. If the increase is greater than the decrease, we will regard it as beneficial, or we will stop the replacing. And because we can simplify the relation between the increase and decrease as this formula, but we don't know the actual C CPU and C GPU, so we'll use a parameter alpha to instead. And here is an example of our algorithm. Suppose that we have 6 nodes in a graph, and P is their sampling probabilities. We will first sort them according to P, and the ordered nodes list is here. Assume that we have 2 GPUs now, and each GPU can only store 2 nodes. We will first initialize the GPUs with node 1 and node 2, and P sum is the sum of probabilities of new nodes on each GPU. So we'll initialize these two variables of 0, and we need to replace the nodes on GPUs that have smaller P sum every time. Now we will do the replacement. So the first old node is 2, because we will first replace the last node on each GPU. And the first new node should be 3, because it has higher sampling probabilities. And now we will define, we should know whether this replacement is beneficial. And because it satisfies this formula, so this replacement is beneficial, and because P sum 0 equals to P sum 1, so we will replace the node 2 on GPU 0 with the node 3. And we will update the p sum 0 also. And notice that we need to keep at least one copy of node 1 and node 2, so that the next old node will be node 1. And we find this replacement is also beneficial, and p sum 0 is greater than p sum 1. So we replace the node 1 on GPU 1 with node 4. And because there's only one copy of both node 1 and node 2, we'll finish this algorithm. However, our algorithm based on the assumption that the access frequency is scaled. So if the access frequencies of nodes are less scaled and the GPU memory is small, the data loading might be also expensive even with our algorithm. Because in this situation, we still need to load many nodes from CPU in most of the cases. So we further propose a locality-aware neighbor sampling technique to reduce the data movement overhead. The basic idea is to scale the access frequencies of nodes that stored on GPUs. Suppose we have 6 nodes and they are stored on 2 GPUs and CPU. And if we want to increase the access frequencies of nodes 1, 3, 2, 4 of the input layer, we will first need to directly scale them in this layer. And but the nodes in the former layer have impact on these nodes in input layer. So we also need to increase the access frequencies of their neighbors in the previous layer. But we will only scale a set of them here because the increase in the probabilities of many nodes cannot concentrate the memory accesses to a small set of nodes. So in this case, if we scale, because the neighbors of 1, 3, 4, 2, 4 are all the nodes from 0 to 5, if we scale all the nodes here, actually, if we calculate the new sampling probabilities, they should be the same. So our locality-aware neighbor sampling method will be useless if we scale all of them. And we will scale these factors with an adjustable factor. And this factor is initialized of 1 and multiplying with 2 if the data loading time is still more than 20% of the total execution time. But we set a maximum of this factor. So it will be not large it will be not too large. And this is the experimental setup of our work. For platform, we use a single machine with 2 GPUs and 2 CPUs and 8 GPUs. We use 2 types of GPU interconnections. The first one is that every 2 GPU are connected with NVLink bridge. And the second one is all GPUs are connected with NV switch. We use 5 datasets and they are Reddit, Yelp, Products, Papers, and Mag. We can see that the feed size of Mag is about 175 gigabytes. We use 4 baselines. If partitioning directly partitions the graph based on the node index, and random partitioning divides the graph into several parts randomly. And we also use Matisse and paragraph partitioning as our baseline. This figure shows the speed up on Reddit. The .1n means that we can store 10% of the nodes on each GPU buffer, and .2n means that we can store 20% of the nodes on each GPU buffer. And let's see the results on 2 GPUs with 0.1 and buffer size. We can see that the data loading time of naive takes 50% of the total time, and paragraph slightly decreased the portion to 48, and the Metis decreased this portion to 44, and which is also an unacceptable number. Our method can decrease the data loading time to 38 of the total, 38% of the total execution time. When using larger buffer size 0.2n, which means that we can store more nodes on GPUs, the data loading time of each method will decrease. But even with our method, the portion of the data loading time is still about 30. So we apply locality-aware sampling here, and the results show that we can only use 20% of the total execution time for data loading. And the results are similar on 2+2 GPUs and 4 GPUs. For large graph papers, our method also shows speedup. Paragraph cannot finish partitioning papers in 5 hours, and Metis partitioning aborts due out-of-memory errors. So we compare our method with naive and random partitioning. Random and naive partitioning shows similar results on different GPU settings. And our method outperforms these two with all settings. Overall, our strategy reduced the data loading time by 2.4 times to 4 times compared to random. To show how locality-aware sampling affects the training process, we compare the training loss of different sampling methods with all GPU settings. Here we use an adaptive scale factor with maximum value of 8. In this figure, we can see that our method has similar convergence speed with original, and we even have smaller loss at the end of training. The results are similar with 2+2 GPU and all the other settings on other graphs besides the Reddit. And it indicates that the data loading of the locality-aware sampling will not affect the convergence speed when scale factor is small. And also we find the corresponding accuracy of our method is also comparable with the original. Besides reducing data loading time, another advantage of our technique is that our algorithm is much faster than the previous graph partitioning algorithms. And this table shows the execution time for dividing the graph into 4 parts on 3 datasets. We can see that paragraph spends much longer time than both DGL and our method. And our algorithms also outperforms DGL. This is because that paragraph has big O and squared times complexity, but we have only big O n time and also the space complexity. So finally, to summarize our work, we first aim to reduce the data loading overhead for large-scale GN training on multiple GPUs. And based on our observation, we propose a performance model of data movement among CPU and GPUs, and then provide an efficient algorithm to find an optimal data placement strategy. For those cases that our strategy not works very well, we propose a locality-aware neighbor sampling technique to further reduce the data loading time overhead. And our experiment shows that we can reduce the data movement overhead by 1.2 times to 3.3 times with the data placement strategy. And we can achieve up to 4.4 times speed up with locality-aware sampling. And so these are all the contents of my talk. So thanks for your listening.